Hey everyone, and welcome to today's Explainer. We're going to jump right in because today we're decoding some of the absolute most essential and honestly frequently misunderstood keywords in the entire Java language. You know, if you've ever stared at a screen full of Java boilerplate code and thought, what is actually going on under the hood here? Well, you are in the exactly right place. We're setting the stage today to master Java's structural keywords. Specifically, we're talking about static and final, and we're going to do it without all the usual textbook confusion. We'll see exactly how these keywords control your memory, enforce strict rules, and basically make your programs infinitely more robust. Let's get to it. Okay, let's dive into this. Here is our quick roadmap for today. First up, the static memory saver. Then we'll cover the rules of static methods, followed by final, the constant keyword. After that, we'll solve the mystery of main and wrap up by unpacking string array args. All right, part one, the static memory saver. Let's talk about optimizing that heap space. So to truly get a grip on our first keyword, we kind of need a real-world scenario. Imagine you're building a massive college application system, and you're creating a bunch of student objects. You know the drill. Each student has a name, an age, a roll number, and a college name. Now ask yourself this. What if you have 100 students, or even 10,000 students, and literally every single one of them goes to the exact same college? Let's just say it's IIT Guwahati. If we just write our code the standard way, every single time we instantiate a new student object in Java, we're creating a brand new field in memory for the college name and writing IIT Guwahati into it, over and over and over again. Now, this is a massive inefficiency. When objects are created in Java, they live in this space called the heap memory. And a string reference takes up, let's say, about 4 bytes of space. So you create 100 student objects, you've just copied that 4-byte string 100 times. You're completely clogging up your heap memory with 400 bytes of just highly redundant data. To put that into perspective, if you scale that up to thousands of students, that wasted space snowballs fast. Why are we copying and pasting a value that literally never changes between students? What if, instead, we could just extract that college name, drop it into a single shared space, and just have all 100 students point directly to it? Well, enter our memory-saving hero, the static keyword. The moment you declare a variable as static in Java, you are fundamentally changing its ownership. It doesn't belong to any individual object instance anymore. It belongs to the class itself. By just slapping the word static in front of our string variable, we completely elevate the college name from an instance variable, meaning a personal detail, to a class variable, a shared truth for everybody. Suddenly, your heap memory is totally spared, and your program is instantly way more efficient. Now, what's really interesting about this is how a static block runs. You see, because a static variable belongs to the class, it actually gets loaded into memory the second the class itself is loaded by Java. That's way before you even create your very first student object. A static block is basically this specialized chunk of code that runs exactly once to initialize these shared variables. It sets up the whole shared space perfectly before your application even really gets out of the gate. Moving right along to section 2, the rules of static methods. Let's look at the boundaries we have to follow. So the power of static isn't just for variables. We can absolutely use it on methods too. Imagine you've got a function like mark attendance. If the logic for attendance is exactly the same for the whole class, it makes total sense to make that method static, so you can call it without even needing a specific student object. But every powerful tool has boundaries. So what are the boundaries of a static method? To really get this, you have to remember one core logical constraint in Java. You simply cannot access what hasn't been created yet. Because static methods live at the class level, totally independent of objects, they operate in a very restricted world. Let's break down the 3 main rules. Rule number 1, a static method can only directly call other static methods. Rule number 2, it can only access other static variables. Think about it. If our mark attendance method tried to look up a student's non-static name variable, Java would just throw an error. It has no idea which student's name to look up because there's no object. And rule 3, which is absolutely crucial, a static method cannot use the this keyword. This refers specifically to the current object instance. No object, no this. The JVM literally wouldn't know what this refers to. All right, part 3, final, the constant keyword. Let's completely pivot to a new problem here. We've optimized our memory, sure, but how do we protect our data from accidental mutation? I mean, one of the absolute biggest headaches in programming is when a value you rely on gets unexpectedly changed by some other part of your code. Take a classic math constant, pi. 3.14. Imagine you're building a massive engineering app, and halfway through, some object accidentally reassigns pi to 3.16. Actually, scratch that. If it gets changed even slightly, absolute chaos ensues. Your calculations are completely wrecked. We desperately need a way to tell Java, do not ever let this value change under any circumstances. And that is exactly where the final keyword comes in. Final is the ultimate lock. When you apply final to a variable, you are telling Java that once a value is assigned, it is a constant. It stays fixed forever. If anyone even attempts to write code that reassigns a final variable, bam, hard compiler error before the program even runs. It is your ultimate shield against accidental mutation. Just a quick pro tip on this. When you do make a variable final, there's a standard industry naming convention you really should follow. You write the name in all uppercase letters, separated by underscores. Something like pi_value. It's a massive neon sign to other developers that this is a constant. Plus, you can actually team up our two heroes. If you declare a variable as static final, you get the whole shebang, a permanent read-only constant that is shared universally across your entire class. Super efficient and totally secure. Which brings us to part 4, the mystery of main. Why is it always static void? Okay, get ready for a major aha moment. We are finally going to deconstruct the single most famous line of Java boilerplate out there, public static void main. I mean, every Java developer has typed this literally 1,000 times. But how often do we stop and ask why it's written exactly like that? Why must the main method always be static? If you delete the word static, the whole program just flat out refuses to run. To crack this mystery, we have to look at it from the perspective of the JVM, the Java Virtual Machine. That's the engine that's actually starting up your code. So the crucial point here is the JVM's logic sequence. Step 1. When you launch an app, the JVM immediately hunts for the starting line, the main method. Step 2. Since your code hasn't even run yet, no objects exist. The JVM can't just magically invent an object of your specific class out of thin air. It just wants to execute the code. Step 3, and this is the magic part. Because main is marked as static, the JVM doesn't even need an object. It calls the method directly from the class level, basically shouting, hey, class demo4, run your main method right now. Without static, the JVM would just sit there, hopelessly waiting for an object it doesn't know how to build. Finally, part 5, unpacking string array args and terminal inputs. So here we are at the very last piece of that boilerplate puzzle. Right inside those parentheses of the main method, we always see string array args, an array of strings. Why does Java force us to have this, even if we're just printing a tiny hello world? Well, to get it, we have to rewind a bit. Back before we had these beautiful graphical IDEs with one-click run buttons, developers ran everything straight from the text-based terminal, and they often needed to pass in configurations or data right as the program launched. They'd type a command like Java Demo 5, and then follow it up with a bunch of parameters like aditya, tandem, rohit negi. And this brilliantly illustrates exactly what happens behind the scenes. The JVM takes whatever extra words you typed into that command line, bundles them all up into a neat little array of strings, and passes them right into your main method as that args array. So the word at index 0 is aditya, index 1 is tandem, and so on. Now, sure, we don't pass names like this much anymore, but this is still heavily used today in huge modern frameworks like Spring Boot to pass deep system configurations right when a server boots up. Wow, okay, we have covered a massive amount of architectural ground in this explainer today. You've seen exactly how static optimizes your memory by bumping data up to the class level. You know the strict boundaries of static methods. You've discovered how final permanently locks your data down. And we've finally solved the mystery of the static main method and those command line arguments. You now have a seriously profound understanding of Java's core structural pillars. So, the only real question left is, now that you literally control memory allocation and data security at a master level, what unstoppable applications are you going to build next? Thanks so much for hanging out with me today, and keep building amazing things.